we really start getting into exponential functions. And so, learning target 4, you're going to be graphing exponential functions. And then the other half to this lesson is solving some basic exponential equations. So, graphing and solving, pretty standard lesson here. So a few things that we need to review before we get started in our example problems. Number one is, what are some of the basics that you need to know about graphing exponential functions? Well, first of all, I'd like you to recall that the parent function, or the basic thing for exponential functions, is y equals a times b to the x. And I want you to kind of compare this to our old friend y equals mx plus b. Remember slope-intercept form. M was the slope. It was the number that we added or subtracted each time to get to the next number. And b was the y-intercept, the number that you started at, or the y value when x equaled 0. Well, we have a lot of connections here for exponential functions. So a is going to wind up standing for the y-intercept, just like b was kind of the y-intercept over here. And then in this case, b is called the rate, which is analogous to the slope. If the slope is the number that you added or subtracted by to get to the next number, well, the rate is the number that you multiply by to get the next number. And so, here, you would be adding a negative to go down, to make your graph go down. Here, well, a negative isn't going to necessarily work, but if I am multiplying by a fraction like 1/2, that's what's going to make it go down. So you'll see in some examples today that anytime you've got a rate that's less than 1, you're going to have something called decay. It's going to be a graph that goes down. Here's some other things that you're going to need to know. Let's see. Well, if the y-intercept is the y value when x equals 0, here's why a is the y-intercept. Well, if x equals 0, well, then I would have anything here, whatever the rate is to the 0 power. Well, anything to the 0 power is 1. And then a times 1 is whatever a is. And so that's why a is going to be the y-intercept. It's the y value when x equals 0. And then the other thing is that, well, we know that we've got the parent function, the basic version here, but every other function that we've done this year, we've done a shift with. And so we have that in this case as well. And so we can say y equals a times b to the x minus h plus k. And so this will move it left and right. The h value will move the function left and right, and it'll be, again, the opposite of the sign. So if it's positive, it'll move it left. If it's negative, it'll move it right. And this plus k will move it up and down, and this will be the same as the sign. So if it's positive, it'll move it up. And if it's negative, it'll move it down. And so if you remember some of the other functions that we've worked with, like a parabola, there was always a key point that we would use for a parabola. It was the vertex. When on the parent function, that was right there at 0, 0, and so we kind of moved that around. When we had circles, the key point was, again, the middle, and we'd have that circle, and we would move the center of that circle left, right, up, or down. Well, with exponential functions, that key point is actually at 0, 1. So the reason for that is typically on the parent function, this a value will be 1. And then you'll have a y-intercept of 1. And so the original version would look something like this. And then you would just kind of take this original point, you'd shift it left, right, up, down based on your h and k value. And then you would pretend like you had y equals a times b to the x without the h or the k, and you just graph it there. So that's a strategy that we're going to use here in this lesson. A couple other things. Compound interest. hopefully we know what interest is. Simple interest is found, interest is the principal times the rate times the time. But this is, when it's just compounded simply. So in most cases, we have compound interest. And so the amount, or the final amount that you're going to have in your account, not the interest, but the final amount, including the interest, is the principal, the amount that you started with, times 1 plus the rate times time. And this is compounded annually, but there are other ways that we can compound things, semi-annually, quarterly, monthly, daily. And when that happens, what we'll do is we'll simply take principal times 1 plus, be the same up till here, but now we're going to just take it and the rate and divide it by n, and then take the time and multiply it by n. And so n stands for the number of times that it's been compounded. And so we'll talk about that. Now, there's one other thing here, dealing with compound interest, or taking compound interest. We talked about kind of the progression here, semi-annually, or I guess this would be annually, semi-annually, quarterly, monthly, daily, hourly, minutely. Well, we can actually have something that's called compounded continuously, where it's always compounding. And one of the things that we have to do in order to use that is this e value. So if you remember, e is not a variable, it's a number. It's 2.718 ... It's an irrational number like pi. But here's where you get it from. We take this equation right here, or this one, and we just say, all right, we're gonna have an initial investment of $1, and it's going to be have a rate of 100%. So you're going to get 100% return on your investment, n times per year for 1 year. So this winds up giving us the function a equals the principal, which is 1, times 1 plus the rate, which is 100%, so as a decimal, 1, divided by n to the n times t, but t is 1, so it would just be n. Okay, and so what happens here as we plug in values for n, what we'll notice is that this hits a limit. If I plug in 1, I get 1 plus 1 is 2 to the 1 is 2. So when n equals 1, the amount equals 2. But then as this number gets bigger and bigger and bigger, what you'll see is it approaches the limit. So as n, get to like 1,000, okay, you get something like a equals 2.71 something or other, and it just gets exponentially closer and closer to this number right here. And so why would we use this? Well, we use this in the compounding continuously model, and that is the amount, if we compound it continuously, is p times e to the rt. So here we're using that e value, 2.71, and then the rate and the time are up there. All right, well, let's take a look at some examples. It says graph each function, we'll do that, and then graph the function of y equals 2 to the x for comparison. Give the domain and range. So here, this one's a little bit tricky. You might think, if you remember earlier, we said, you can't have a negative rate. Well, this actually isn't a negative rate, although it kind of looks like it. What this is -1 times +2 to the x. And so we can see here that my y-intercept is going to be -1. And then I just multiply by 2 to get to the next number. So -1 times 2 is -2, and -2 times 2 is -4, and -4 times 2 is -8. And so we get this function right here. If I went the other way, instead of multiplying by 2 to go this way, I divide by 2 to go this way. And so -1 divided by 2 is -1/2, and you can see enough of a pattern here to be able to connect your dots and draw your graph. Compare this to y equals 2 to the x. Well, again, this would be like saying y equals 1 times 2 to the x. And that means your y-intercept would be 1. You would multiply by 2 to get to the next part. And so we can see that in this case, we divide by 2 to go this way. And we wind up with just the mirrored thing over here. So when your a value is negative, it's going to be the same as the original. It's just going to be reflected over the x-axis, like so many of the other functions that we've looked at. All right, well here, again, it's like saying 1 times 2 to the x plus 3. So here's what we're going to do. We're going to take this plus 3. We know that moves it left. So if this was our original kind of key spot, okay, we're moving that to the left 3. And then we're going to pretend like that's kind of 0, 1, and then do the rest. So again, I'm just going to pretend like I'm graphing y equals 2 to the x, like essentially like this spot right here is the origin. So I would multiply by 2 to get to the next number. So it would be 2. And then the next one would be 4. Next one would be 8. If I wanted to go left, I'd divide by 2. So I'd go like that. And there it is. That's how that function looks. And then comparing that to y equals 2 to the x, well, we know what that looks like from over here. You can see that each spot has just been shifted left 3. Let's see. For this one, we've got both parts. We're going to shift it, this key spot, 0, 1, 2 to the right, and then 1 down. Okay, so it's actually kind of like this right there is the origin. So if I go over 1, I'd be up 2. Over 2, I'd go up 4. Let's see, so it'd be right here. And then I'd be up 8, which would be right here. I'd go left and go half of that, half each time. So there it is. Okay, domain is going to be all real numbers for all of them. They go forever left, forever right. The range, however, we'll say all real numbers y is greater than 0. It never actually gets to 0, so we don't want to put or equal to. Same thing here, all real numbers y is greater than 0. But of course here, my range is a little bit different. We still say all real numbers y, but this time y is greater than, well, this time my asymptote is at -1. So -1. All right, let's solve some stuff. We'll start with maybe one of the more basic ones here. One of the tricks that you can use is to simply wind up with making the same base for both sides. So if I said 1/3 to the x, well, that would be the same thing as 3 to the -1 to the x. So remember, 3 to the -1 is the same as 1 over +3. And then over here, I could say this one is 3 to the 4th. That would be the same thing as 81. And, well, I could just kind of continue here, and this would be 3 to the -x if I multiply these two things, exponent to an exponent, and then 3 to the 4th over here. Well, if I have the same base, I can do a little trick where I just essentially just kind of cross those out, and I get -x equals 4, and so that means x equals +4. All right, this one over here, I'm going to do the same trick, but it's a little bit more advanced of a version. I've got 2 to the x plus 4, and then over here, this could be like 2 to the 3rd to the x minus 6th. And so what I'm going to do here, again, I have an exponent to an exponent, so I can basically do the same trick where I cancel out the bases, and I have x plus 4 is equal to 3 times x minus 6. And of course, this winds up being a pretty easy equation to solve. I do the distributive property, and let's see, I'll add the 18 to both sides, And then over here, I got 2x, divide both sides by 2, and x equals 11. All right, over here, there's a number of different ways, actually, that I could solve this one. I'll show you kind of my preferred way. If I have x to the 4/3, well, the inverse or opposite of 4/3 is 3/4. So 4/3 times 3/4 would be 1, and so I would just get x. But of course, what I do to one side, I have to do to the other side. So I take 81 to the 3/4. So that's really what I've got to do here. And so I remember a little bit about taking a number to a fractional exponent. And so this would actually wind up being the 4th root of 81 to the 3rd power, where the 4th root of 81 is just going to be positive or negative 3 to the 3rd, which winds up being positive or negative 27. All right, so there's a few examples on how to solve exponential equations. Now, a big part of this is just being able to do practical questions. So here is kind of one of the ways that we can do that. And of course, we're using the compound interest stuff. So suppose $1,000 is deposited into an account paying 4% per year, compounded quarterly. Okay, so that's 4 times a year. That means n is going to be equal to 4. Find the amount in the account after 10 years, again, assuming you're not withdrawing anything. So here's our formula. We got A equals the principal, the original amount, $1,000, times 1 plus the rate. Well, the rate is 4%, so 0.04, divided by the number of times I compound it or pay it out, which would be 4 here. And then I take that to the 4 times t, which is 10, so 10 years. All right, well, let's figure all this out. 0.04 divided by 4 would be 0.01, plus 1 would be 1.01. So I got 1,000 times 1.01 to the 40th, 4 times 10. Don't forget that you need to do exponents before you multiply. So you're doing all this on your calculator. Hopefully you wind up getting $1,488.86. So remember, that's the total amount, not the interest. The amount that you've made in interest is simply $488.86. So that answers this question right here. All right, let's see maybe a little bit different version. You got this person, Becky, who must pay a lump sum of $5,000 in 5 years. So she's got to pay somebody $6,000 5 years from now. What amount does she need to deposit today, or what is the present value, if she's getting a 3.1% interest rate compounded annually that will grow to $6,000 in those 5 years? Well, she wants that future value to be $6,000. We want to know how much she's originally investing, so that's going to be our variable. And we got 1 plus, and then this is just compounded annually, so there's no, it's not quarterly like the last one, so we'll just say 0.031, and then 5 years, so to the 5. Well, let's see, this all kind of boils down to, we got 6,000 equals P, and then this would be 1.031 to the 5th, and then 1.031 to the 5th is just going to be 1.1649 about, and so then we will divide both sides by this 1.1649, and we get P, the original amount, is $5,150 and about 66 cents. So that's what she would have to invest originally, so that in 5 years at this rate she would wind up with that $6,000. Let's see. So this next part, if she only has $5,000 now, she needs $5,100, but she only has $5,000. What annual interest rate should she invest in? So she's going to have to increase the rate that she gets in order to make that $6,000. So here's how this one will go. We'll say, all right, she needs that final amount to be $6,000. She only has $5,000 to invest now, so that's the principal. 1 plus the rate, well, this time that's the variable that we need to figure out. The time is still 5 years. So now we're on a mission to solve for r instead of p. Well, the first thing I'm going to do is I'm going to divide both sides by 5,000. And on the left, I get a nice little 1.2. And then on the right, I wind up with 1 plus r to the fifth. All right, well, I can think of this as kind of like if I want to get rid of that to the fifth, I could take that to the 1/5 power or to the 0.2 power. So if I do that, that cancels out that to the fifth, and I just have 1 plus r. And then over here, I'll take this to the 1/5 power. I'll do that on my calculator, and I get about 1.0371 when I round. At this point, I subtract the 1 from both sides, and I get r equals 0.0371. And then turn that into a percent, I'm going to get 3.71%. So she would need to increase that 3.1% to 3.71% so that her $5,000 turns into $6,000. All right, well, that's it for lesson 2.